Okay, we have a couple of expressions to expand, and then a few expressions here to simplify. And we have the rules. Okay, I've written down the rules for exponents, at least the rules that we're going to need to do these. So I'm going to set this over here. And let's start with 3a squared b cubed the fourth. Now, the way at least one person wrote this out is like so. These are columns. But, 3a squared is 3 times a times a, and then times b cubed is a b times b times b. Raising that to the fourth, we've got to do it 4 times. Well, now we know that we can rewrite these. We can put all the a's together, all the b's together, and the 3's together. And knowing that, and review what we did last time if you don't understand that. But this is going to be 4 3's. So 3 is going to be multiplied 3 times 3 times 3 times 3. You got that here. Then you got a times 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 a. There are 8 of them. So that's a to the 8th. And then we have 3, 6, 9, 12 b's. So that's b to the 12th. Okay, so this is by the main concept. Okay, very good. So this is by the concept or by definition. Now, we can also do it by the rule. Okay, and the rule is this one. Now I've only written it for 2 quantities, an x and a y, but we could have any number of quantities here raised to the c power. Just like we did here, we had 3 quantities that were raised to the 4th power. Here we got those 3 quantities raised to different powers. Okay, so if we use this rule, we can immediately see that this is, well, that's just 3 to the 1st power. So that would be 3 to the 1 times 4, or just 3 to the 4th. And then a raised to what power? Well, if you got something raised to the a to the c, you multiply those powers. Okay, so that's 3a to the 2 times 4. And then b is raised to the 3rd, but then that's raised to the 4th power. That's b to the 3 times 4. And look at what we do. A is raised to the 2 times 4. Well, look here, we got a raised to the 2nd times a raised to the 2nd times a raised to the 2nd times a raised to the 2nd. How many of those? There are 8 of them. That's 2 times 4. So we have 2 a's 4 times, 2 times 4 a's. And we have 3 b's 4 times, b to the 3 times 4. Now we can always visualize this, even when the numbers, even when the powers are big as they will be in the next one. Okay, in the next we're not going to be able to write it out so many times. We could, but be a waste of time. We use this rule. Anyhow, when you multiply 1 times 3, that's just 3 to the 1, 3 to the 4, sorry. And a to the 2 times 4, 2 times 4 is 8. And b to the 3 times 4, that gives us b to the 12. Same thing that we got here. Oops. Here. We didn't have to write all this stuff out. Okay, so let's take the next one. We have x squared y z to the fourth raised to the 70th power. Well, I could write this out, x times y times z times z times z times z, and I could do that 70 times. If I did, how many x's would I have? Well, I've got 2 x's in each one, and they're going to be 70 of them. That's 140 x's, okay? You can visualize that, or you can just use the rule. You should be able to do both. You should understand why the rule works, so you don't forget the rule or get mixed up. We got x to the a to the c, y to the b to the c. So that's x to the ac, y to the bc. So we have x squared to the 70th is x to the 2 times 70. Y is just to the first power, so we write that as y to the 1 times 70. And z is to the 4th power to the 70th. It's going to appear 4 times 70 times. And again, when you look at this, you can see, yeah, if I wrote all these out, I'd have 4 z's in each one, but I'd have 70 of them listed. So I have, excuse me, I get all choked up when I talk about exponents. Okay, now you'd have 4 times 70, right? Again, you'd have 4 of them in each string. In 70 strings, it's called a string, okay? You should have 4 times 70. Okay, well, that's the reason for the rule. That gives you x to the 140th, y to the 70th, z to the 280th. Which is exactly what you got. And you obviously wrote that down without writing down all the strings. You didn't write down 70 strings, so you applied the rule. Okay, so you understand this rule, and of course we understand this rule. This rule kind of follows from this one and one other rule. Right like this. Okay. And these rules are slightly different than the way I wrote them last time. Okay, there are a number of ways of writing it. The way I wrote them last time is a little more elegant, but this might be a little bit easier to apply. Okay, so that's good. Let's try some of the others. Okay, now we did quite well on this one. Some people wanted to go ahead and write this out: x cubed y squared times x cubed y, and so forth, or x times x times x times y, and do that 4 times. And you saw immediately that if you do this 4 times, you're going to get 12 x's. See, you wrote them out all that way. Now, let's see how the rules apply. Okay, because the rules tell you to do exactly the same thing you did without having to write it all out. So x cubed y squared to the 4th, using the same rule we used here and here, is x to the 3 times 4 times y to the 2 times 4. And then this is x to the 5 times 5, y to the 7 times 5. Okay? And that's how you worked it out. You didn't exactly write it out this way, but it worked. Okay? Make sure we understand how the rule tells us this. Again, we multiply the a by the c, in this case the 3 by the 4, and we multiply the b by the c, in this case the 2 times the 4, and then we do the same thing over here. Okay, while we do the multiplication, we have x to the 12th, y to the 8th, x to the 25th, y to the 35th. Well, you've got an x to the 12th and an x to the 25th. You're going to add the 12 and the 25, and you saw that immediately. I think some people probably visualize 12 x's and then 25 x's and know that you're going to add these. Okay, so that's good response. So that's going to be x to the 12 plus 25. And of course, that's exactly what this rule tells us. X to the a times x to the b is x to the a plus b. So here's x to the a, here's x to the b. We add the a and the b. And then we have y to the 8th times y to the 35th. That's y to the 8th plus 35th, because we got 8 up here and 35 up there. We add that. And this gives us x to the 37th, y to the 43rd. It's very good that everybody got that without having to write it all out, but being able to visualize it. And then let's make sure we connect it to the rule. Okay, so that's pretty good. Okay, well, what about the next two? See what you get there. Okay, now the last two, and everybody seemed to have gotten these, which is very good. Because the second one, you can't do it just by writing it out. You have to use the rule. Okay. Now, technically, you could write it up. Let's just look. Okay, so we got x to the 30th times x to the 50th. Now, for a rule, well, you multiply the same base, the two numbers with the same base, but with different exponents, which means you've got to have a of these and b of these, which gives you a plus b of these. And that's exactly what you have here. And you can visualize it. You could write out 30 x's and then you could write out 50 x's. And you know, you'd end up with 30 plus 50, and that's 80. So this is x to the 30 plus 50, which is x to the 80. That's very good. And then x to the 7th times x to the negative 5th. Well, that's x to the 7 plus negative 5. You add the exponents. Of course, when you add a negative 5, that's the same thing as subtracting 5. So that's x to the 7 minus 5, which is x to the 2nd power. Okay, so that's quite good. Now we want to do more with negative powers because the next assignment is on negative powers. So you already got the idea, but it can get a little more complicated than this. Still, we're using the same rules. Okay. So let's see, what would you get for x squared times z to the negative 5th raised to the negative 2nd power? If you use the rules, it's easy to do this, but it doesn't look quite like it did before, so it might be difficult to figure out how to use the rules. See if you can do that. Okay, now if you try to write this out, you write x squared as x times x, but how do you write z to the negative 5th? It's not z times z times z times z times z times z. I think maybe I did that too many times. It certainly isn't. But it would be the reciprocal of that. It'd be 1 over z to the 5th. Okay. So that's what it means, but we probably want to make it simple. It's much simpler to use the rules. So by the second rule, what's the second rule tell you? I'm sorry, the fourth rule. What's the fourth rule tell you should do here? Okay, now apply this rule. And let's just write out the rule. Using x and z instead of x and y, because it doesn't really matter what we call these, right? It's going to work for x and g just as well as it would for x and y. And this is raised to the c. This is x to the ac times z to the bc. Okay, and then we can identify the numbers a, b, and c. It's x to the a, so a is 2. B is the power of Z, that would be -5. And C equals the power up here, -2. So using this values of A, B, and C, x to the AC would be x to the 2 times -2. And Z to the BC would be Z to the -5 times -2. All that should make sense. So again, we've done x to the second to the -2. There's x to the second, x to the 2 times -2. That's when we raise the power, we multiply powers. Z to the -5 to the -2, it's Z to the -5 times -2. This equals then x to the -4, Z to the 10th. And that's what you got if you did the multiplications correctly, okay? So whether you did or not, 2 times -2 is -4. -5 times -2 is a +10. Now there's another way to write this. This would be 1 over x to the 4th multiplied by Z to the 10th. And then that would be the same as 1 over x to the 4th. That should be 4th, not 5th, times Z to the 10th over 1, just to be sure that we see how the numerators and denominators line up. And when you multiply two fractions, you just multiply the numerators. 1 times Z to the 10th is Z to the 10th, and x to the 4 times 1 is this x to the 4th. Okay, now we have two forms of this, okay? So you can say that x to the second, y to the -5th, raised to the -2nd power equals x to the -4th, Z to the 10th, which equals Z to the 10th over x to the 4th. These are both valid expressions. You can be asked to simplify this expression or expand it and write it this way or this way. This way would be without denominators because there's no denominator here. Okay? So okay, so here it is, written without denominators. And here it is, without negative exponents. Two different forms. Okay. Now you usually want to either write it this way or this way. If it's not specified, you can pick whichever way you want to write it. Okay. Well, let's do something a little bit more challenging. We'll kind of leave it as this, as far as this topic goes. Let's say we got x cubed y to the -7th over z to the -3rd raised to the -2nd power. How would we write that? Okay, now, didn't have time to have everybody work this out in detail, but what are we going to do? Okay, well, x cubed y to the -7th to the -2nd is x to the 3 times -2, and y to the -7th to the -2 is y to the -7 times -2. That works out just like it did up here. Okay, same thing. And then it's got to be over z to the -3 times -2. You might need a little more explanation of that. I think you get it from open math. Okay, then we just multiply the exponents. We get x to the -6th, y to the 14th, divided by z to the 6th. And now we have both negative exponents and denominators. So we want to write this first without negative exponents. That's going to be y to the 14th. X to the -6th is 1 over x to the 6th. So x to the -6 will become x to the 6th in the denominator. Then we have z to the 6th. Now another way to write it is without denominators. Z to the 6th down here in the denominator is the same as z to the -6 in the numerator. So we have x to the -6, x to the -6, y to the 14th, z to the -6. Both of these are valid. This is without negative exponents, and this is without denominators. So we could even say, okay, without denominators, we have this. Without negative exponents, we have this. Okay, well, there's more, and there are more complications you can get, but let's see if we can get this much. Now, I want to do a quick introduction to polynomials. So, how much more I can see. Okay, so let's say we have x cubed plus 2x squared minus x added to 3x to the 4th minus 5x cubed plus 3x. Okay. Now we should understand that we can only add like terms. So we could add the x cubed to the -5x cubed. Okay. Now we don't have anything over here to add to the x to the 4th. So it's going to stay the way it is. So we're going to have 3x to the 4th. We usually list the highest exponent first. Okay. 3x to the 4th. And then we're going to have plus x cubed minus 5x cubed. So we list our x cubes next, and then we list our x's next. That'll be minus x plus 3x. Okay. Well, 3x to the 4th doesn't add to any of these because x is raised to the 4th power, and none of these are. None of these have an x to the 4th, so we just have 3x to the 4th. But we do have x cubed and a minus 5x cubed. So that's a 1x cubed and a minus 5x cubed. That gives us minus 4x cubed. And then we have minus x plus 3x, which is plus 2x. So when we add these, this is what we get. So you can use this as an example. You might want to go back over my explanation, or you might refer the explanations you see in open math. Okay. So now, a little terminology. This 3x to the fourth is the highest power. You call that the leading term. That's the highest power. The degree of the leading term is the exponent. So the degree is 4. And we also call that the degree of the polynomial. That's a very important characteristic of the polynomial. Now, what do I mean by polynomial? I mean a bunch of powers of your variable. Okay, a bunch of multiples of your powers. Okay, so just so many x to the fourth, so many x cubed, so many x's, and so forth. Okay. So it's pretty easy to get the idea of adding polynomials. Multiplying polynomials is a little more complicated because you have to use the distributive law. So the distributive law says that A multiplied by B plus C is A times B plus A times C. This is something everybody should be familiar with because you get that even in pre-algebra. It might be a little bit fuzzy, so we'll be sure we do it pretty carefully and explicitly. And also, if you do A plus B multiplied by C, that's the same as AC plus BC. Again, this should be familiar. You get plenty of explanation in open math if it isn't. And of course, next time we can clarify if we find that there's a problem with this. Okay. Now, if you multiply, let's say 2x plus 3y times 4x plus 5y, what do you get? Well, you use the distributive law, you actually use it twice. Use the law in this form where we have an A plus B multiplied by C. Now here's your A plus B, and all this is your C, because all this is getting multiplied by your A plus B. So you're going to write this as 2x multiplied by 4x plus 5y, and then plus 3y multiplied by 4x plus 5y. Okay, that's the distributive law. It's this times this plus this times this. Now we have this multiplied by this plus this. Well, it's going to be this times this plus this times this. That's going to be 2x times 4x plus 2x times 5. Right? And that's what we get here. Over here, we're going to get 3y times 4x plus 3y times 5y. Again, applying this law. This is your A, and here's your B plus C. And that's A times B plus A times C, as we say here. That's what we have. 2x times 4x. Well, from what we've done with exponents, we're pretty confident that that's going to be 8x squared. 2x times 5y. Well, 2 times 5 is 10. X times y is xy. And then 3y times 4x. Well, 3 times 4 is 12. And y times x, I'm going to write that as xy because it doesn't matter in which order we multiply. Officially, be y times x. That's equal to x times y. So I'm just going to write it as x times y. Then we have 15y squared. Okay, then we don't have any more x squared terms, so we can't add the 8x squared to anything else. So we just have 8x squared. However, both of these are xy terms, so we can add them. We got 10 xy's here and 12 xy's here. We add that, we get 22 xy. And then we have 15y squared that can't be combined with anything else. This is pretty much all you need to do the homework. Okay? Only two things. You can only add like terms and different powers are unlike. Okay? You can't add different powers. You can multiply them, but you can't add them. You've seen how to multiply them with the rules of exponents. You got this thing called the leading term here, and the degree of the leading term is the exponent in the leading term. It's the highest power term. And that's also called the degree of a polynomial. I didn't write that down, but you'll see it. So that's how we use the adding of like terms, let's say. The distributive law is actually officially distributive law of multiplication over addition. There are other distributive laws, but this is the one we're going to be mainly focused on in this course. Okay. We can use that to multiply the sum of two terms by the sum of two other terms. Okay. And that's how we did it. So that's really all you need to know. Now you get more explanation. You'll see videos with more examples, but it's all you need to know in order to do homework. Okay.